Imagine you are an A320neo pilot.
Okay.
It is July. You have just landed at a notoriously congested airport, like JFK or Heathrow.
Oh, yeah, that tarmac is just radiating heat.
Exactly. And you are staring down a 20-minute taxi sequence just to get to your gate. The ground control frequency is just a chaotic wall of sound.
Right, and as a professional, you're constantly managing the aircraft's energy state.
Yeah. So one of the most standard procedures you will execute here to conserve fuel is a single-engine taxi.
Standard operating procedure.
You shut down engine number 2, relying entirely on engine number 1 to push the aircraft along the pavement. But you're sitting in that cockpit, the sun is beating through the windows, and the cabin temperature in the back is starting to creep up.
Uncomfortable for the passengers.
Very. You have one running engine feeding one air conditioning pack, and it is struggling. So the temptation is right above your head on the pneumatic panel.
Oh, I know where this is going.
You think about reaching up and switching the crossbleed valve to open, just to let that one running engine feed both packs and blast some cold air into the cabin.
But you really shouldn't.
Right. If you touch that switch, you trigger a cascading mechanical crisis. I mean, you could easily blow a baggage cart across the apron or, ironically, completely knock out the very air conditioning you were trying to boost.
Leaving everyone sweltering while you deal with a master caution.
Right in the middle of a complex taxi clearance.
Huh.
So, welcome to today's deep dive. We have a
Wow.
really fascinating document in front of us today, an excerpt titled A320neo Crossbleed Logic and Single-Engine Taxi Constraints.
It is a great piece of technical literature.
Okay, let's unpack this. Our mission for this deep dive is to explore exactly why A320neo pilots are strictly restricted from opening the crossbleed valve during a single-engine taxi.
And how that perfectly illustrates the incredible balancing act of thermodynamics, physics, and ramp safety that pilots manage before they ever leave the ground. It is a brilliant constraint to analyze. And if you take a look at the backdrop we have pulled up behind me, this intricately detailed schematic of the A320neo's engine architecture and pneumatic system, you begin to see the hidden geometry of the aircraft.
It's complex.
Very. Operating this jet isn't merely about memorizing the manual or running through a checklist blindly. It is about understanding the structural and thermodynamic compromises that the engineers had to make. Every system on this aircraft is highly interdependent.
And that interdependence is exactly what we are going to tear into today. Let's establish the baseline operational rule for the flight deck.
A golden rule here.
Right. When a crew is conducting a single-engine taxi, the crossbleed valve must remain in the IU-22 position. The pilot cannot manually force it to open to allow the running engine to supply bleed air to the offside pack.
It sounds like an arbitrary software rule.
Yeah, but it is actually deeply rooted in the physical hardware of the Neo variant itself.
What's fascinating here is the underlying thermodynamic engineering that forces this rule to exist. To understand it, we really have to look at the massive physical differences between the older CEO, the current engine option, and the NEO.
Right, the new engines.
Exactly. When Airbus decided to re-engine the A320 with these new, ultra-efficient, high-bypass geared turbofans and LAV engines, they ran into a severe real estate problem. These new engine cowlings are physically massive.
So they couldn't just bolt them onto the existing mounts?
No. To maintain the required ground clearance under the wing, they had to completely redesign the pylon architecture.
So they are structurally beefing up the pylon,
Yes.
changing its aerodynamic profile to handle a heavier, larger diameter fan.
Right, and trying to keep the engine from scraping the runway.
Which means the internal volume of that pylon, the space where all the plumbing and systems live,
Yeah.
that gets compromised.
Precisely. And the primary casualty of that redesigned pylon architecture was the pre-cooler. As a necessary structural compromise, Airbus had to install a pre-cooler with a significantly reduced physical footprint compared to the older models.
And because it is smaller, it inherently has a drastically reduced heat exchange capacity,
Exactly.
which creates a massive bottleneck. Because the air bleeding off the high-pressure compressor of these engines is incredibly hot.
Scorching.
And the pre-cooler's entire job is to function as an air-to-air heat exchanger, dropping that temperature down to a manageable level before it hits the packs. So let's play out the scenario.
Okay.
What actually happens thermodynamically if our hypothetical pilot on that hot JFK tarmac decides to ignore the restriction and manually opens the crossbleed valve?
It creates an immediate, severe thermal overload.
Just instant.
Yes. By opening the crossbleed to feed 2 packs from a single engine, the pilot is suddenly demanding double the mass flow of high-pressure bleed air.
Wow.
All of that extra volume is now forcing its way through a single undersized precooler. The heat rejection demand spikes instantly.
But the real kicker here is the energy state of the aircraft at that exact moment. They are on the ground.
That is the critical factor. The aircraft is performing a taxi. The single running engine is operating at ground idle, generating just enough thrust to keep the plane rolling.
So the fan isn't spinning very fast.
Right. Because the fan speed is so low, there is very little bypass air being scooped up and channeled across the precooler to act as the cooling medium.
So you have a scenario where the thermal demand from the bleed air has doubled.
But the cooling supply from the engine fan is at its absolute minimum.
It is a recipe for an immediate thermal runaway in that localized system.
Completely.
And the aircraft's computers aren't just going to sit there and let the pneumatic ducts melt. The cooling capacity gets overwhelmed in a matter of moments, which triggers an overheat condition.
And then the alarms start.
Exactly. The pilot is sitting there navigating a busy taxiway, and suddenly the screen lights up. They get an AirNG 1 or 2 bleed fault warning. The master caution chimes.
And to protect the structural integrity of the system, the bleed valve automatically slams shut.
It's a severe, instantaneous penalty. The pilot's attempt to simply increase the cabin cooling results in the complete loss of all air conditioning and pressurization from that engine.
The packs shut down entirely.
And think about the human factors nightmare that creates on the flight deck. You are trying to manage ground control frequencies, watch for ground traffic, and suddenly you have a fault demanding your attention.
You have to run the procedure, reconfigure the panel.
Figure out how to reset the system, all while the cabin behind you is rapidly heating up because you now have zero ventilation. It is a massive spike in workload caused by misunderstanding the physical limitations of that smaller pre-cooler.
It highlights why systems knowledge is so paramount, but the thermal limitation is really only one half of the equation.
Here's where it gets really interesting. This isn't just an internal plumbing problem or a comfort issue. Flipping that crossbleed switch actually alters the external physical threat profile of the aircraft on the ramp.
It does, and it all comes down to the revised pneumatic duct routing on the NEO.
Right.
Because of those same architectural changes to the pylon and the wing root that we just discussed, the ducts carrying the bleed air from the engine to the packs had to be routed differently.
It's not a straight shot.
No, this new geometry is more tortuous, there are more bends, and it creates significantly higher air pressure losses between the engine bleed ports and the pack flow control valves.
So by the time the air navigates that maze of ducting, the pressure has dropped. And if a pilot opens the crossbleed to feed both packs, the pressure drop becomes even more pronounced across the manifold.
Exactly. And the FADEC, the Full Authority Digital Engine Control, is constantly monitoring that duct pressure.
It's the brain of the engine.
Right. When it sees that the pressure arriving at the packs is insufficient to meet the demand of 2 packs running simultaneously, it intervenes. The engine essentially realizes it is starving the pneumatic system, so it automatically compensates.
The FADPD commands the engine to work harder just to overcome the friction and pressure losses in those specific ducts.
Yes. The engine control system will automatically increase the ground idle thrust of that single running engine by approximately 2 to 3% N1.
Now, to someone outside the aviation industry, a 2 or 3% increase in rotational fan speed sounds like a rounding error.
Barely noticeable, you might think.
But on A320neo, with those massive high bypass fans, that is a colossal amount of energy.
If we connect this to the bigger picture, you have to visualize the operational environment on a congested airport apron. You have ground crews, baggage handlers, fuelers, and catering trucks constantly moving in tight proximities around these aircraft.
It's a busy place.
Very.
Yeah.
And there is an established expected hazard zone behind an idling A320. When that FADC automatically spools the engine up an additional 3% N1 just to push air through the air conditioning ducts.
The velocity and volume of the exhaust wake expand exponentially.
The jet blast hazard becomes severe and, more importantly, entirely uncommanded by the pilot's thrust levers.
The pilot's hand is completely off the throttle, yet the engine is spooling up. You are talking about enough localized force to easily flip a luggage cart or knock ground personnel completely off their feet.
Easily.
And then there is the FOD, risk foreign object damage. The sheer suction force at the front of the cowling and the blast at the rear can pick up chocks, tools, or debris from the tarmac and turn them into projectiles.
Threatening other multi-million-dollar aircraft parked adjacent to the taxiway.
It fundamentally degrades the safety margins on the ramp. Ground handlers are trained to respect the standard idle danger areas, But this sudden automated thrust increase catches people off guard.
A simple, localized decision inside the flight deck to improve passenger comfort translates directly into a violent physical hazard 50 feet behind the tail.
It is a stunning example of unintended consequences. You are trying to cool down the cabin, and suddenly you are an active threat to the ramp operation. And that brings us to the ultimate irony of this specific constraint.
The fuel.
Yes. The entire philosophy behind performing a single-engine taxi is economic efficiency and environmental stewardship.
Right.
The airlines mandate these procedures to shave off fuel consumption and reduce carbon emissions over the course of thousands of fleet cycles.
Fuel flow at ground idle is carefully optimized. But when you introduce that thermodynamic and pneumatic demand, you ruin the math.
Right, because if the pilot opens the crossbleed, forcing the FADC to spool that single engine up by 2 to 3% N1 just to run both packs, they push that engine completely out of its optimized ground idle fuel burn curve.
The relationship between N1 thrust and fuel flow isn't perfectly linear. Pushing a high bypass engine slightly higher out of its lowest stable idle state requires a disproportionate amount of fuel to maintain that higher rotational mass.
So that single engine is now working against the restrictive duct routing, gulping extra jet A to maintain the pressure. So what does this all mean? It means the economics completely fall apart. The data shows that the extra fuel burned by that single engine operating at an elevated N1 just to feed 2 packs is virtually identical to the fuel you would burn if you just left both engines running at their normal, minimum stabilized idle.
It renders the entire procedure pointless. You endure the asymmetric taxi characteristics. You risk overloading the pre-cooler and losing the packs entirely. You create a massive jet blast hazard for the ground crew.
And at the end of the day, you haven't actually saved a single drop of fuel.
It is the definition of an illusory efficiency. The physical constraints of the NEO simply dictate that one engine at idle cannot efficiently or safely support the pneumatic load of the entire aircraft.
Which brings us back to the flight tech reality. Airbus standard operating procedures are uncompromising on this. The SOP explicitly mandates that the single operating engine only feeds its respective pack, period.
The manual doesn't leave room for pilot discretion here because the margins are too tight.
But we still have to address the operational reality that pilots face every day. We can analyze the engineering constraints all afternoon, but that doesn't change the fact that it is a sweltering afternoon in Miami. The aircraft is heat-soaked from sitting at the gate, and boarding is complete.
Right. The passengers are strapped in, the doors are closed, and one single air conditioning pack operating at ground idle simply does not have the cooling capacity to prevent the cabin temperature from rising to uncomfortable or even unsafe levels.
The pilots are staring at their screens, knowing they need the cooling capacity of both packs, but they also have a company mandate to perform a single-engine taxi for fuel savings.
It seems like an impossible bind.
You either sacrifice passenger safety and comfort, or you sacrifice fuel efficiency by starting the second engine. But Airbus procedures offer a highly specific workaround that bypasses the pre-cooler bottleneck entirely.
Instead of opening the crossbleed and trying to bleed the main engine dry, the crews rely on the APU,
The auxiliary power unit.
It is incredibly versatile in this specific scenario. It isn't just for starting the main engines or providing electrical power at the gate. During a single-engine taxi on a hot day, the APU becomes the primary pneumatic source for the offside pack.
It completely changes the pneumatic architecture. The pilots leave the crossbleed in AUDO, ensuring the running main engine is isolated and only feeding its side. Then, they keep the APU running during the taxi sequence.
The APU bleeder is routed directly into the manifold to feed the second pack.
By utilizing the APU, the pilots brilliantly sidestep every single hazard we just discussed.
Yeah, the APU's bleed air doesn't pass through the main engine's pre-cooler, so there is zero risk of overwhelming that system and triggering a bleed fault.
And because the main engine isn't sensing a massive pressure drop across the ducts from trying to feed 2 packs, the FADE leaves the main engine at a true minimum ground idle.
There is no uncommanded spool up, no 3% N1 increase, and therefore no sudden jet blast hazard threatening the ground crew.
It is a masterclass in load distribution. The main engine handles the thrust required to taxi the aircraft and the pneumatic load of 1 pack. The APU handles the pneumatic load of the second pack.
The cabin pulls down to a comfortable temperature. The pre-cooler operates well within its thermal limits. The ramp remains safe.
And even with the APU burning a small amount of fuel, the net economic gain of the single-engine taxi is preserved.
It perfectly illustrates the tightrope walk that A320neo pilots perform while they are supposedly just driving the plane to the runway.
They are managing the physical limits of the redesigned pylons, mitigating the severe thermal constraints of smaller pre-coolers, actively protecting the ramp workers outside their windows, optimizing razor-thin fuel economics, and balancing all of it against the immediate comfort of the passengers sitting behind them.
And the fulcrum of all that complex, multi-layered decision-making is the position of one single crossbleed valve on the overhead panel.
It is incredible.
This raises an important question about how we perceive modern aviation. We board these incredibly sophisticated machines, and we expect a seamless, comfortable environment. But the reality is that the flight deck is constantly engaged in a highly dynamic negotiation with the laws of thermodynamics.
Understanding a highly specific constraint like single-engine taxi logic pulls back the curtain on just how demanding the operational environment truly is.
The pilots aren't just following a route. They are managing thermal loads, pressure differentials, and energy states with incredible precision.
It really shifts your perspective on what is happening up front. So we want to leave you with a final thought to mull over. The next time you are sitting on a taxiing aircraft on a sweltering summer day, looking out the window and listening to the steady, powerful hum of the air conditioning above your head, think about the immense, hidden thermodynamic math happening in the cockpit just to keep you comfortable.
Absolutely.
The pilots are actively preventing internal systems from melting down and protecting the ground crew outside, all while threading the needle on fuel efficiency. It makes you wonder what other invisible boundaries of physics, aerodynamics, and engineering are pilots constantly bumping up against and navigating around in the pursuit of a perfect, uneventful flight. Thanks for joining us on this deep dive. We will catch you next time.